In the last class, we have seen the time-ordered functions in quantum mechanics. So we'll just find the analog of the time-ordered functions in quantum field theory. So here we have to replace the appropriate dynamical variable in quantum mechanics with proper dynamical variable in quantum field theory. So in quantum field theory, the endpoint function will be the vacuum that is defined here in interacting theories, phi of x1, phi of xn, right? So here this will be the object x, okay? So this can also be written in the path integral form, which is integral d phi, then this object e raised to I action divided by the path integral d phi e raised to is. So this is the master formula for the path integral. And we have the boundary condition, okay, that we impose in quantum field theory, which is phi of t comma x will go to 0 as t go to plus or minus infinity or x going to infinity, right? So this will be the boundary condition. The generating functional in quantum field theory is defined as z of j is equal to integral d phi e raised to I s. S is the action, which is a function of phi, plus I integral d for x j of x phi of x. And we can also write the general expression for the ratio z of j by z naught is equal to time ordering of the exponential I integral d for x j of x phi of x. Right? So as you expand this in power series, you have powers of phi in terms of time ordering. And here z naught is our generating function at j equal to 0. Okay. So this is the general expression for calculating the endpoint function in any theory, okay, in any scalar theory. And this is the power of the path integral formalism. So before going to the interacting case, let's first discuss the free field theory. First we will discuss free field theory, and then we will see how to accommodate the interactions in this free field theory. See, almost identical to harmonic oscillator case, as you get a quadratic Gaussian integral without any higher powers. So the Lagrangian in a free scalar field theory can be written as minus half partial mu phi minus half m square phi square. Okay, so here the Lagrangian is almost identical to the harmonic oscillator, and the action is minus half integral d for x prime phi of x, then k x prime phi of x prime. So we have seen that k x prime in quantum mechanics it was k t t prime. So here it is k x x prime is equal to minus partial square plus m square minus I epsilon times the Dirac delta x minus x prime. Okay. Here this epsilon is related to the epsilon prescription as discussed before. So this is related to the epsilon prescription. Okay, I can write the generating functional integral d phi e raised to minus, so here it is is, so action I have to write here, so minus I by 2, because I then minus half k phi k prime plus I j phi. So I am using the shorthand notation here. Okay, shorthand notation, and this is equal to c by root of determinant k exponential I by 2 j k inverse j, and z naught is equal to c by root of determinant k as usual. So we find k inverse x x prime is equal to IGF x x prime, right? And z of j divided by z naught, so this 2 will get cancelled and we have e raised to I by 2 j, then k inverse is IGF. I can substitute IGF, so I and one more I will be minus 1, I square will be minus 1, so j GF j. Okay, so now if you calculate the endpoint function, then you get identical form of endpoint function in quantum mechanics, right? So this will be GF x1 x2 GF x3 x4 plus GF x1 x3 GF x2 x4 plus GF x1 x4 GF x2 x3. So the Wick's theorem also applies here, and everything else also gets passed on to the scalar field theory in quantum field theory, right? Now we'll see interacting theories. So this was just for a scalar field theory, free field theory. Now we will include interactions. Interacting theories. So the simplest case of interaction is the Lagrangian is equal to the Lagrangian of the free scalar field theory. Then I will add some interactions which is of higher order. So in free scalar field theory we have a quadratic potential. So something higher than that will be the quartic potential, right? Then I can write Lagrangian of the free scalar field theory plus Lagrangian coming from the interaction, right? But the thing is that here the general interaction coming from the general interaction will contain only terms with phi and not the derivative of phi. Okay, so here you can see this is the simplest example and you can see there are no derivative of phi. So this interacting term will only be a function of phi, or Li depends only on phi and not on phi dot. Okay. Therefore, the Hamiltonian can be written as free theory Hamiltonian plus the interacting Hamiltonian. Okay, and the interacting Hamiltonian can be directly written as the integral of d cube x Lagrangian of interaction, because there are no derivative of phi involved. Therefore, I can directly write the interacting Hamiltonian from the interacting Lagrangian density. Okay. And similarly, once you get the Hamiltonian, then the action will be the free theory action plus the action coming from the interactions, and the action is equal to integral d4x Lagrangian density of interaction, or in other words I can also write minus integral dt hi. So the reason for this is simple, okay, because the interacting part does not contain any time derivatives. Okay, the interacting theory does not contain any time derivatives in the field. It is only dependent on the field phi. Therefore, I can simply write the interacting action as minus integral dt hi. So we are interested in finding the endpoint function. Okay, so we are always interested in finding the endpoint correlation function in the interacting theory, right? Phi of xn omega. And gn can also be written as integral d phi, right? The time ordering e raised to is divided by integral d phi e raised to is. So these path integrals are not doable, right? They are not doable because you have non-quadratic terms, because s is s naught plus si, and in si you have non-quadratic terms. So you have only you can easily do the integration if it is only Gaussian. Gaussian means it should be quadratic, but here you have non-quadratic terms in the polynomial, and we don't know how to do such integrals for a system which is not a harmonic oscillator, right? So we don't know how to do the integrals for a system which is not a harmonic oscillator. Therefore, we have to treat it perturbatively. Okay, so such systems you have to treat perturbatively. So we treat the Lagrangian of the free scalar field theory as the main term and Li as the perturbation. Okay, and Li is equal to lambda to the power lambda by 4 factorial, right? So here and 5 raised to 4, this lambda is taken as very small, okay, so that you can use the power series approximation. So this will be the perturbation. This is the main term and you have a perturbation. Fine. Then if that is the case, Gn is equal to integral d phi. You have the time ordering. Then e raised to is. So is can be written as is0 isi, right? The free theory part and the interacting part divided by integral d phi e raised to is naught e raised to isi. Okay, so this time ordering function times e raised to isi can be another x. It can be considered as another x. Then again you can write it as free theory, right? So here you can write, you can consider these two time ordering and exponential e raised to I si as another x. So you can, then what is remaining? Then the remaining thing is d phi e raised to I s naught and this x. Okay. And this x is actually the product of the time ordering and e raised to I si. So again, this can be considered as another time ordering in free theory. So in free theory, I can write this as time ordering of e raised to I si, right? I can write like this, and divided by, in the denominator I have in free theory, time ordering of e raised to I s interaction 0, right? So here also I have integral d phi, right? So this e raised to is0 e raised to I si. So I can treat this as a new function, and the remaining thing will be the time ordering in the vacuum, ordinary vacuum. So I can write like this. So here this is the vacuum in field theory. Vacuum in free theory. So in essence, I have written the vacuum in interacting theory in terms of the vacuum in free theory. Okay, and there will be the interaction term sitting in the time ordering. So this expression relates the correlation functions of an interacting theory in terms of those in free theory. Okay, so this can be evaluated in free theory by expanding the power series and using Feynman diagrams. So this is a clever way of doing it. This expression relates correlation functions of an interacting theory in terms of those in free theory. So whenever there is time ordered exponential, it has to be expanded in power series. Then you have to do the time ordering of a bunch of factors, right? So here I have exponential. Whenever there is time ordered exponential, it has to be expanded in power series. So e raised to x I can write as 1 plus x square by 2 factorial plus etc., right? The power series expansion. So I expand the above equation in power series of Si. So I can write Gn as, okay, first I will write the numerator. Okay, first I'll write the numerator. Then I have to write time ordering of x, right? Then minus I integral dt. I have time ordering of x hi, right? Plus etc. Other terms will also be there, 1 by 2 factorial plus etc. And in the denominator I have 1 minus I integral dt 0 time ordering of hi plus the other terms. So how did I get this one? E raised to I si will be 1 plus I si plus etc., right? Which is equal to 1 plus I. What is the action? Action will be integral dt, right? Integral dt of hi minus hi. So minus I integral dt hi plus etc. So this multiplied by an x bar is also there, right? X bar multiplied by e raised to I si. And in the denominator you have only e raised to isi. There is no x bar multiplied. Right? So I have to substitute it here. First I have to expand the exponential and then multiply with x bar in the numerator. Denominator you just have to expand. There is nothing to multiply in the denominator. Okay. So when I do like this, I will get, when I multiply with x bar, then here there will be an x bar, right? Here also there is an x bar. So I will get something like this, which I have written here. Okay. Fine. Now here, let this term, that is 0 time ordering of x bar, okay, this is the free theory endpoint correlation function. Okay, so it's a endpoint correlation function in free theory. So I have to denote it by the symbol Gn of 0. Okay, so let this is equal to Gn of 0. So we always assume that interaction is very small, okay, and therefore do the Taylor expansion of the denominator also. So in the denominator you have 1 minus something, right? So when you do the Taylor expansion in the denominator, that is the binomial expansion, then I can write 1 minus x whole raised to n as 1 minus nx, right? So if I have something 1 minus x whole raised to minus 1, then it will be 1 plus x, right? So I can apply the binomial expansion in the denominator also, because we treat the interaction as very small. Okay, and wherever there is this term, I replace it with Gn of 0. Then in the next step I can write Gn 0, because here first term is Gn 0. So Gn is equal to, right, Gn is equal to Gn 0, then minus I integral dt, right, 0 time ordering of x bar hi, okay, plus etc. So this is the numerator, and in the denominator I apply the binomial expansion so that this will go to the numerator. So 1 plus I dt 0 time ordering of hi 0 plus other terms is also there. Okay, so the first bracket multiplied by the second bracket, that is Gn. So expanding, so I have to multiply now these two brackets, right? So expanding, I will get Gn 0 plus I Gn 0 integral dt 0 time ordering of interacting Hamiltonian, right? Then minus I integral dt 0 time ordering of x bar interacting Hamiltonian, right, plus other higher order terms. Now from here onwards, if I keep on multiplying, then you will get square, cube, etc. So I'll just write higher order terms. Okay, so this is Gn, that is endpoint function in the interacting theory. I am writing it in terms of the endpoint correlation function in the free theory plus the perturbations, right? So these are all perturbation. So these are first order perturbation and these are higher order perturbations, and eventually I will neglect the higher order perturbations. I will only restrict myself to the first order perturbation. Okay, so these are the first order full first order terms which I have written down here, which is the correction to the free theory. Okay, so I have written the endpoint function in interacting theory as a correction to the endpoint function in the free theory. So free theory plus some corrections. Fine. So these are the full first order terms, which is a correction to the free theory in endpoint functions. So all these terms in free theory can be evaluated using Wick's theorem. So that is why I am representing everything in terms of the free theory. Okay, so I'll call this equation as equation number 1. Okay, so it is essential to develop some techniques to evaluate such series of terms. It is not a difficult thing to do, but in practice the calculations will become more and more tedious, right? So if you see, this is not very difficult to do, but you have to sit and do for each term, and the calculations will become more tedious, and the efforts to simplify this task has led to the Feynman diagrams, right? So how do I write each term like this? I don't have to sit and write. I can just use Feynman diagrams so that, and there are some tricks called as Feynman rules, so using which I can easily write down all these terms. Okay, so what are Feynman diagrams? Let's see Feynman diagrams. Right? Feynman diagrams. So far we have discussed the general equations that can be applied to any interaction. Now let's look at a specific case. The simplest case will be minus lambda by 4 factorial 5 raised to 4. Okay, for the simplest case we consider the 2-point function, right? And 2-point functions are the Feynman functions. So we consider only 2-point. For the simplest case we consider only the 2-point correlation function. Okay, so x1 and x2, only up to x2 we will consider for simplicity, and 2-point functions are called as Feynman functions. So g2 is nothing but Feynman function, so that's very easy. So this will be time ordering of phi of x1 and phi of x2, right? So this is 2-point correlation function. Now I have to plug in this equation number 1, right? I have to plug in equation number 1 here. So I will get this is equal to gf0 yf, because 2-point correlation functions are Feynman functions, so I can write gf directly, x1 minus x2 plus I gf0 x1 minus x2 integral d4x, right, t. So I am plugging in this equation. So integral d4x, till this I have written. Now time ordering of interacting Hamiltonian, right, this term, time ordering of interacting Hamiltonian. What is interacting Hamiltonian? It was time ordering of, what is hi? Lambda by 4 factorial 5 raised to 4, right, minus I lambda by 4 factorial integral d4x, right? I have just taken out the lambda by 4 factorial term, so inside the time ordering I will have phi of x1, phi of x2. Why this? Because this is x bar, so x bar multiplied by interacting Hamiltonian. So x bar is phi of x1, phi of x2 in 2-point function, and hi will be phi raised to 4 x, right? And the other terms are here. Lambda by 4 factorial is here outside, right? 0 plus other higher order terms. Now we have seen only first order perturbation in lambda. There will be lambda square also, which are all higher order perturbations. Okay. So all the terms in this expansion can be evaluated by repeatedly applying the Wick's theorem, right? I can apply Wick's theorem, and final results will be of the form sum over products of gf of 0 plus some integrations, right? For example, if you have something like this, 5 raised to 4x, time ordering of 5 raised to 4x, okay, then there are 4x available here, right? 5 of x, 5 of x, right? 4 times. So how do you pair? I can pair these two, right? I can pair these two. Then I can pair these two. I can pair these two, right? So I can write this combination as 3 times integral d4x gf x minus x gf x minus x, or I can also write this as gf0 of 0 because x minus x is 0, so this whole square, right? I can also represent this as 3 integral d4x square. So this is how I apply the Wick's theorem. So why 3 here? Because the number of permutations it can take will be 3. Because I have 1 phi of x. If I fix this one, then it can commute with other 3 phi of x. There are 3 ways for the permutation, right? That's why I have written a factor of 3. Fine. So likewise, I have to write for g2 of x1 minus x2. This entire term I have to write. This is just an example for one term. Similarly, I have to write for all these terms. So let's start writing. g2 x1 minus x2 is equal to gf x1 minus x2, right? Because it's Feynman function, which is equal to gf of 0 x12, okay, plus, so first term will be, see here it is x1 and x2, so that there is only one way you can do it. If you have a point x1 and x2, there is no other way of permutation. So I just write gf0 x12 plus I lambda by 4 factorial, then gf0 x12, right? And there is a time ordering of 5 raised to 4, which we have already obtained as 3 times integral d4x gf0 of 0 whole square minus, next term will be I lambda by 4 factorial, then gf0 x12, then, so this is the third one, right? So 1, 2, third one. So here also phi x1, phi x2 I have written as, this I have written as gf x12. Okay, so remaining you have 5 raised to 4x. So I will write 3 times gf0 square, right? That is one way of doing it. Then I lambda by 4 factorial. If I don't take this x1 and x2 outside, if I also allow it to permute with x, that is, I see in this case you have phi of x1, phi of x2, then phi of x, phi of x, phi of x and phi of x, right? So these are the points that we have. If you see here, see you have phi of x1, phi of x2 and phi raised to 4x, right? So I have to do the permutation between these 6 objects. There are 4 objects here in phi raised to 4 and then 2 objects outside, phi of x1 and phi of x2. Okay, so I have 6 objects with me and I have to do the permutation for all these 6 objects. So how do I do? So first I have written, okay, these 2 will pair up. Okay, these 2 can pair up. That is only in one way it can pair, right? So that is gf of 0 x1 2. Then the remaining phi of x can do in 3 ways. So that is this. Okay, that is one way of doing this. Then otherwise phi of x1 can pair with x, phi of x2 can pair with this one, and then these two can pair in one way. Okay, so I am going to write, so I lambda by 4 factorial, right? So how can this do? X1 and x2 can do in 3 possibilities, and once this x1 pairs with x, right, then this x2, I'll just do it once again for clarity. Okay, so in the second case, if this phi of x1 is pairing with this phi of x, right, then phi of x2 can go with 1, 2 or 3 choices are there, right? So initially I have phi of x1 which can pair with either this phi of x or this phi of x or this phi of x or this phi of x. So that can happen in 4 ways multiplied by, if it has chosen any one phi of x, then for this phi of x2 has only 3 choice, either this, this or this. So 4 multiplied by 3. So here I have 4 multiplied by 3 integral d4x gf. Here x1 will go with 1x and x2 will go with 1x, and the remaining x will pair, plus other higher order terms in lambda square. Okay, so we have 4 phi's and there are 3 different ways to group them. So we have to include a factor of 3 here, 4 multiplied by 3. So this can be represented diagrammatically. So this is the analytical expression, right? So how do I represent this analytical expression in a diagram? Okay. So let's start with x and y. Okay. So here we are only treating first order perturbation, therefore I need only x. If I am treating the second order perturbation also, then I have to square all of this, right? So I cannot use x anymore. In second order perturbation there will be x and y. So here this is only first order perturbation, so I use only x. Fine. So Gn can be written in the diagrammatic way. So what is the first term? First term is gf0 x12, which means there is a connection between x1 and x2. Okay, so first one will be very easy. I can write Gn is equal to, so you have x1, you have x2. So this is gf0, right? gf0 of x1 minus x2. So this way you represent the first term. Now second term, this plus, what is second term? I lambda by 4 factorial. So I'll just write I lambda by 4 factorial. Then here I have gf x1 x2 also, and 3 times this one also is there, right? So how do I represent this? So 3 I am writing it here. Gf of x1 x2, again same way I can write x1 x2. Then I have integral d raised to 4x gf of 0 whole square, that is gf x minus x. So x has to interact with x itself, right? X has to, so if I have x here, it has to interact with itself how many times? 2 times because there is a square here, right? If you see here, there is a square, gf of 0 whole square. So it has to interact with itself 2 times. So this is one interaction with itself and this is another interaction with itself. Similarly, you have the other term minus I lambda by 4 factorial, right? 3 multiplied by 4 multiplied by 3, right? Then, sorry, this term. I lambda by 4 factorial gf0 x1 2 3 times, same thing. So here also I have x1 x2 x1 x2, right? Then again x interacting with itself 2 times plus, what is the last term? I lambda by 4 factorial 4 multiplied by 3. So I lambda by 4 factorial 4 multiplied by 3. Then integral d for x, then 1 interacting with x, 2 interacting with x and x interacting with x. Okay, so I have to represent this in the diagrammatic form. So 1 interacting with x1 with x, x2 with x and x with x, all in one diagram I have to represent, because all these interactions are coming in the same integral. So I cannot split it into 2 or 3 figures. In one figure I have to represent all these interaction, x1x, x2x and xx, because these are propagators coming in under the same integration, right? So I have to, first I will do x1x. So I have x1, I have x and I have x2. So x1 has to interact with x. So this is the interaction between x1 and x. Then you said I need an interaction between x2 and x. So there is an interaction between x2 and x. Now x has to interact with itself. So x has to interact with itself and all the interactions are in a single diagram. So this is the diagrammatic representation for this analytical expression. If this is the analytical expression, then this will be the diagrammatic representation plus higher order terms in perturbation, lambda. So here you can see the second term and the third terms are exactly equal and opposite in sign, so they will cancel. So the remaining terms will survive, right? Okay, so we have already seen them. These two terms will cancel here also. See here plus I lambda by 4, here minus I lambda by 4. So already these two terms cancel, and in the diagrammatic representation also they will cancel. So each hi in the time ordered function will give an interaction vertex. So this is very important. So what is a vertex? If you have something crossing like this, right, then you get a vertex. Okay, so we call this as interaction vertex. This is called interaction vertex. If you are having a first order interaction, then in the analytical expression you have a term with hi. If you are having second order perturbation, then you will be having hi square. If you are taking third order perturbation, you will have hi cube, right? So we usually ignore all the higher order perturbations. We only treat the perturbation in the first order, which means that there will be, in the analytical expression, there will be hi present, right? So there will be hi present, which we substitute as integral, this one, interaction, integral d for x lambda by 4 factorial 5 raised to 4x. If there is one interaction Hamiltonian present, then it will give one vertex. So you can see we have treated all the perturbation in first order only, right? Therefore, in all these diagrams, we have only one vertex. If you see here in the second term, if you see, here you have one vertex here at the center, right, x. And also third term, here you have one vertex. And the fourth term also you have one vertex. And if you consider the higher order terms, then you will get 2 vertex, 3 vertex, etc. So here I am considering only in first order, therefore there is only one vertex present here. Okay. So in practice, drawing this diagram is much easier than counting all the possible contractions. And from this diagram, we can write down the analytical expression. So once you have this diagram, you can always write this analytical expression. So that is the easier way, right? So first, always we draw the diagram, and from the diagram, you can always write the analytical expression. So these diagrams are called as Feynman diagrams, and the expressions can be obtained from the diagram through a set of rules known as Feynman rule. Okay. So we can try an example from second order. So second order, in the sense, lambda square terms will be there, right? So there will be many terms with lambda square. I'll consider only terms with hi square and lambda square. So there will be a term, if I expand in the second order perturbation, I'm not writing all the terms, there will be a term that contains 1 by 2 factorial minus I lambda by 4 factorial whole square integral d4x d4y. Why I am writing x and y? Because this is second order perturbation. So I have to multiply 2 perturbations. So first perturbation hi will give hi of x, and the second perturbation hi of y. So that I can multiply to get hi square. Okay. So I am just representing it by x and y because this is second order perturbation. So I am just writing one term, okay, to show you an example for the diagram. So how to draw the diagrams. For that, I am just taking one term in the second order perturbation, which is t phi x1 phi x2. This is the time ordered correlation function, and this is the interaction, phi raised to 4. So this is the interaction. Okay. So here we have x1, x2 and 4x and 4y. So our task is to find all the possible ways to connect all of them. So how do I pair up? X1 can pair with x in 4 ways, right? Similarly, x1 can pair with y in 4 ways. So I have to find all the possible connection between x1, x2, there are 4x and there are 4y. Okay. So it's very easy. First I'll show you how to do. Okay. So there are different possible diagrams. The first possible diagram is that x1 is connected to, and there is one more thing here. This is second order perturbation. So second order perturbation will have 2 vertices. Okay, so you have to remember that, right? Nth order perturbation will have n vertices. Fine. So x1, I have x1, I have x and I have x2, right? So how many x I have? I have 4x. So 1x I have connected to x2, 1x I have connected to x1. So I have 2 more x left. So I have y here. How many y? 4 y's are there. So I am connecting something like this, Okay, and y also like this. Fine. Yeah. So 1, 2, 3, 4, 1, 2, 3, 4. So y with itself, x with y, x with itself, x1, x2. So this is one possible diagram, right? So here I write, because this is second order perturbation, the expansion of the exponential, okay, in the second order will contain a 1 by 2 factorial, right? So e raised to x will be 1 plus x square by 2 factorial plus etc. So we are seeing this one. So always in the second order perturbation there will be a 1 by 2 factorial. In the nth order perturbation there will be 1 by n factorial. Okay. Therefore I am writing 1 by 2 factorial, right? And second order perturbation. So each Hamiltonian will have I lambda by 4 minus I lambda by 4 factorial. So second order means there will be a square because hi square, right? And there is a symmetry in x and y. Even if you exchange x and y, you cannot find the difference because there are 4x and there are 4y. So there is a symmetry between x and y. Therefore I multiply a factor of 2. Okay, this factor is for symmetry. Then x1 can be connected to x in 4 ways. So if I see x1 and I want to connect it to x. So how many x I have? I have 4x. So x1 can be connected to x in 4 ways. So 4. So once one x is connected to x1, then for x2 there are only 3 remaining, right? So x2 to x will be 3. So 4 multiplied by 3. Now if I see from this x point of view, x can be connected to y in how many ways? How many y's are available? There are 4 y available, right? So if I try to connect x to y, I have 4 y's available. Therefore again it can be connected in 4 ways, right? Once that is done, then I can do only x to y again in 3 ways. Only 3 y's are available for any connection for y with x. Therefore I multiply by 3. So in total here I have, if I solve this, I will get minus lambda square, then 1 by 2 square. Okay. Then, so this is one way to connect. There is another way to connect this x1, x2, 4x and 4y. Okay. That is, if I can have x1 here, then x here, y here and x2 here. So x1 I can connect to x, x2 I can connect to y. So one x is already gone and one y is already gone. So remaining 3x and 3y are remaining. So I can have 3 connections. And there are 2 vertices. If you see, there are 2 vertices here. And in this diagram also there are 2 vertices. One vertex here, one vertex here and one vertex here. Because this is second order perturbation. So you have 2 vertices. So here also I have to repeat 1 by 2 factorial because it is second order perturbation. Then hi square is there. So I lambda by 4 factorial square. This comes from hi square. Then here also, even if I exchange x and y, things will not change because there is a symmetry between x and y. So for that I have to multiply a symmetry factor 2, right? Then how can I connect x1 to x? So x1 to x can be connected in 4 ways. So 4. But once I connect x1 to x2, then the remaining x available to connect it to y are only 3. Okay. Then how many ways x2 can be connected to y? It can be connected in 4 ways. But once I connect it in one way, then one way is gone. Then for connecting y to x, you have only 3 ways. sorry, two ways, because one is already connected. Here also we chose one, so only 2 is available, right? Which means minus, I can simplify this to minus lambda square by 3 factorial. Okay, similarly I'll do one more. There are many diagrams possible. I'll do one more for example, okay, because already we are at the end of the class. So one more diagram I'll do. I can connect between x1 and x2, okay. So I don't need a mediator x or y to connect x1 and x2. That can be done independently, and then I can connect x and y, right? So I have 4x available, I have 4y available, so there can be 1, 2, 3, 4 ways of pairing x and y. So there are 2 vertices again, right? There are 2 vertices, interacting vertices. Yes. So how do I write this? Again 1 by 2 factorial minus I lambda by 4 factorial. So these are common for any second order perturbation. You have to just copy these terms. And now x1 can be paired with x2 in only one way. So 1, and x and y can be paired in 4 factorial ways, right? This can be done in 4 factorial ways. So here the term will be minus lambda square by 2, 1 by 4 factorial. Okay, similarly you can have other figures also. I'll just draw those figures. You can calculate the terms later. Okay, so next you can have x1 and x2 connection, and the connection between x and y can be something like this. Sorry, x and y here. So there is connection between x and y with itself, x with itself, y with itself, and connection between x and y. Okay, so this is also possible. There are 2 vertices, interacting vertices will be 2, right? So you can write corresponding terms. Then next one possible is x1 and x2 like this. Then there are 4x available, so 2 are interacting with itself and 2 are interacting with itself. Then so this is x. Similarly I have 4y, so 2 y's are interacting with itself, another 2 y's are interacting with itself. There are again 2 interacting vertices. So this is one possible diagram. Then I have x1, I have x, I have y, I have x2. Okay, so one x is connected to y, one x is connected to x1. So there are 2x remaining. Those 2 can interact with themselves. Now one y is connected to x2, one y is connected to x. So there are 2 y's remaining. Those 2 y's can interact among themselves. So again here you have 2 interacting vertices. So here there is one vertex, here there is one vertex. So these are all the possible diagrams, and you can always calculate the factor. Okay, so this factor like this you can calculate. Okay, so for today we will stop here. We'll continue the Feynman diagram in the next class, how to interpret and how to write the expressions from the each diagram, and the Feynman rules we will discuss in the next class. Okay, so for today we stop.